students, I am Dr. Harisingh. Today I bring you the next learning episode in BSc Forensic Science on behalf of the content writers, myself and Ms. Tulika Banerjee on an important unit of paper Criminalistics, that is Examination of Glass Evidence, its part 2. Now in this lecture we will be studying about the laboratory examination of glass, that is the refractive index measurements and then the elemental analysis of glass. Let us see what we are going to study here. We will study the examination of glass in laboratory, that is refractive index measurements, then we will study the elemental analysis of glass and then we will conclude the lecture. It is actually a forensic scientist's duty to analyze glass fragments so as to clearly and unambiguously determine the origin of a given sample. Now, every material has its own refractive index. As a result, the refractive index measurement can give an actual indication of the composition and the thermal history of the glass. As a result, one can actually know the make of the glass. Now, as we know that a light beam bends from its original path on passing from one medium to another. This process of refraction is thus the basis of different methods for determining the refractive index of the glass. Refraction is much more evident in solids than in liquids or gases. Glass is indeed an excellent medium for showing refraction. Refractive index measurement is affected by the types of glass according to its color, manufacturer and thickness. As it is difficult to measure refractive index by direct method practically, so some indirect methods like immersion methods, dispersion, etc. are used. Definition and use of refractive index measurements. Let us study this now. Now, refractive index is nothing but a dimensionless quantity which is characteristic of an optical medium and is defined as the ratio of velocity of light in vacuum to the velocity of light in the medium. That is, n is equal to c by v, where n is the refractive index of the medium, c is the velocity of light in vacuum and v is the velocity of light in that given medium. It determines how much light is bent towards normal or away from normal, where normal is nothing but the line which is perpendicular to the interface of the two mediums, or in other words, how much light is refracted when the beam enters a material. This is also described by the very famous Snell's law, which is given by N1 by N1 sin 1 is equal to N2 sin 2, where R1 and R2 are respectively the angle of incidence and the angle of refraction crossing the intersurface between the two mediums with refractive indices N1 and N2. This is also described by Snell's law, which is given as N1 sin theta 1 and equal to N2 sin theta 2, where theta 1 and theta 2 are respectively the angle of incidence and the angle of refraction, which is shown in the figure on the screen. Now, here the angle of refraction and the angle of incidence, as you know, as I have already said, are theta 2 and theta 1 in the figure, and normal is nothing but a perpendicular which is drawn at the interface of the two mediums, and according to the Snell's law now, N1 and N2 are nothing but refractive indices of medium 1 and medium 2. Theta 1 is the angle of incidence in the medium 1, theta 2 is the angle of refraction in the medium 2. Now, here the figure shows that nothing but your line or the light is bending towards the normal. So, that means it is moving from a rarer to a denser medium. If it is the other way around, that is, it moves from denser to rarer medium, it will move away from the normal. As I have described just now, the velocity in the figure, as you can see, decreases when a beam of light is travelling from a gas to solid. In other words, the light bends downwards. This allows the determination of the refractive index of glass, that is, how much light is refracted on entering the glass. since refraction is much more evident in solids than in gases or liquids. Thus, glass is indeed an excellent medium for showing refractions. Refractive index is always greater than 1 since the light travels fastest in vacuum. For glass, the range is between 1.4 and 1.7. Refractive index measurement is thus effected by types of glass according to its color, manufacturer and thickness. Temperature affects the density. Density further affects the velocity of light beam as it passes through the sample. And the refractive index is proportional to 1 by T, that means it is inversely proportional to temperature and also inversely proportional to the wavelength. Thus, refractive index gives an indication of the composition and the thermal history of glass. By thermal history, we mean the last set of conditions under which a glass has been cooled from its softened state. Refractive index is the most commonly measured property as precise refractive indices can be measured rapidly on the small fragments found in a casework. It aids in the characterization of the glass. It provides good discrimination potential. It is possible to determine the refractive index of very small glass fragments also, which can be found on the crime scene. Let us now come to the prerequisite for refractive index measurements. The first thing is that the material recovered should be examined to determine if it is glass and then prepare for another analysis. Glass fragments may be crushed to produce sharp edges using a mortar and pestle or a glass crusher. Slides and cover strips should be cleaned prior to the use with the help of solvents such as acetone, ethanol or methanol and a lint-free wipe, thus making sure that the solvent has evaporated before mounting the samples. Since refractive index is a function of temperature, it is necessary to note down the temperature also. Different instruments used for refractive index measurements. Let us come to this now. Now, there are a number of instruments to calculate the refractive index of glass fragments. Some of them are as follows. The first one is a glass refractive index machine, that is GRIM. Now, glass refractive index machine designed by Foster and Freeman, it utilizes the oil immersion temperature or immersion temperature variation method for the determination of refractive index of glass. Then you have refractometer. Now, it is a laboratory or field device for the measurement of refractive index using the very famous Snell's law. Main type of refractometer is ab refractometer. The only thing is that the methods involving an ab refractometer requires pieces large enough to polish. It has got built-in thermometers and requires circulating water to cool the instrument and fluid temperature. Then dispersion can also be measured by ab refractometer. Then we have a hot stage microscope. It has a furnace with a heating element beneath and above the sample, which guarantees the outstanding temperature uniformity in the sample. In the method, using hot stage microscope, the glass sample is immersed in the high boiling liquid. Then comes the phase contrast microscope. Now, phase contrast microscope is an interference microscope which converts phase shifts in light passing through a transparent specimen to brightness changes in the image. Now, phase shifts themselves are invisible, but become visible when shown as brightness with variation. Then you have is a polarized light microscope. Now, polarized light microscope is a microscope which is equipped with two polarizing elements. One of them is the polarizer, which is located between the light source and the sample, while the other one is the analyzer, which is located between the sample and the observer. Now, let us come to the different methods for calculating the refractive index. It is not possible to measure refractive index directly, as it is not possible to practically measure the speed of light as it passes through the glass. So, instead some indirect methods are used. Now, if a piece of glass is immersed in a liquid whose refractive index matches that of a glass, then the glass becomes invisible, as the light that passes through the glass would have the same refractive index. Now, the various methods are based on this particular principle only. Some of the methods are as follows: Imon's double variation method. In this method, the slide containing the glass fragments is immersed in silicon oil. Here, the oil or the liquid is chosen in such a manner that the temperature coefficient of the refractive index, that is dN by dt, that is the variation of refractive index with temperature, must be of the order of 10 raised to power minus 4. It must also be stable within the temperature range to be considered. This slide with the liquid is then inserted into the hot stage and is illuminated using monochromatic sodium light with a wavelength 5890 angstroms. The temperature of the hot stage could be controlled for heating as well as cooling with a precision of almost 0.2 degrees Celsius or better. For taking the observations, a phase contrast microscope is used. For noting down the observations, the refractive index of the oil was kept on changing by varying the temperature of the oil mount and wavelength of the light used until backline disappeared and there was minimum contrast left between the glass and the liquid medium. The temperature at which the backline disappears is considered to be the match point at which the refractive index of the glass equals the refractive index of the oil. There are some advantages and some limitations of this method, which are as follows. Let us first discuss some advantages. The wide variation in the refractive index of the oil reduces the number of oil mounts needed. This is advantageous as a change in the oil involved can damage the grain itself after the matching point is obtained. This method provides a very rapid means of measuring the refractive index of glass at multiple wavelengths. The precision of this experiment is almost from 0.0004 to 0.0006. Now, let us come to its limitations. This method will not be able to actually differentiate between glass samples from different sources with refractive index difference which is less than 0.001. Now comes the backline method. Backline method is a method for determining the refractive index of a transparent particle relative to its surrounding medium. The advantage of this method is that it not only indicates the difference between the refractive index of the glass and the liquid, but also indicates which possesses the higher value. When an object is immersed in a liquid, a bright fringe called backline is observed at the object interface. In this method, the glass fragment under investigation is immersed in a known refractive index liquid. The difference between the refractive index of the glass fragment relative to the liquid is observed. By doing this, a bright halo or a backline is observed. The movement of this backline with respect to the object or the fragment on changing the focus of the microscope indicates the refractive index of the object relative to the immersion oil, that is, whether the refractive index of the glass is greater than or less than that of the liquid. The difference in the refractive index is indicated by the amount of contrast between the glass and the immersion liquid. The fragment is then removed, washed and placed in another liquid with a refractive index closer to the match point. This is repeated until the refractive index of the match point has been deduced, that is, by using a succession of liquids with different refractive indices, the refractive index of the sample can be deduced. The following are the advantages and limitations of this method. Coming to the advantages, this method requires only a microscope, calibrated liquids, the means to calibrate them, that is a refractometer. It helps in rapid sorting of different glass sources, but it has limitations too. The accuracy of the backline method is limited by the visibility of backline. Factors such as object roughness, object inhomogeneity and small object size, it diminish the visibility of backline and the accuracy of this technique. It actually becomes difficult to recover the glass fragment under investigation and then to clean it properly between liquids. As a result, evidence can be easily lost or liquids may get mixed up, resulting in errors in the measured indices. Results can be reported only with a certainty of 0.001. Thus, it does not form a good discrimination between sources. The refractive index of the liquids can vary with the temperature of the liquid. So, the laboratory temperature is to be maintained at a fixed value, else error can be introduced in the system. Now, due to these limitations, automated glass refractive index measurement was introduced. Now, the automated determination of refractive index using oil immersion method along with the phase contrast microscope and a video camera can be done for glass samples as small as 300 micrograms. In this method, the glass fragments should be cleaned with deionized water and ethanol, then dried and crushed in very small pieces of approximately 150 micrometer in size. A small sample is then deposited on a slide and immersed in a micro drop of oil and covered with a cover slip. In this method, also the selected immersion oil or liquid should have temperature coefficient of the order of 10⁻⁴. Also, the oil must be stable across the temperature range under consideration. The slide is then put in the hot stage. Here, the temperature of the hot stage is controlled by a GRIM fitted with a contrast microscope and a video camera. The temperature of the glass is changed in a controlled manner by using the hot stage. The temperature at which the glass disappeared, that is, there is a minimum contrast between the oil and the glass, is recorded electronically, and an average of the match from both the heating and the cooling cycle is converted to refractive index value according to the calibration curve of the oil. The temperature of the hot stage is adjusted in such a manner that the refractive index of the liquid is initially higher than the sample, but during the analysis the instrument lowers down the temperature of the preparation or the hot stage through the match point for the glass. The contrast between the glass fragments and the liquid is observed and monitored, and then the matching point is noted down. This procedure is then repeated as the temperature is now raised through the match point. These values are then recorded as the match temperature on cooling and the match temperature on heating, which are then averaged to give the match point temperature of the given sample. This is then converted to the refractive index value according to the calibration curve. The calibration curve has been obtained by standardization of oils using reference glass with certified values of refractive index. American Standards for Testing Materials recommends a minimum of 3 standard glasses for the calibration for each oil. The following are the advantages and some limitations of this method. Coming to the advantages, the automated method for the measurement of refractive index has the advantage of improved precision as well as improved accuracy. The refractive index is automatically generated and electronically recorded. Over the years, GRIM 1 has been replaced by GRIM 2 and now GRIM 3 is the latest available, but it has limitations too. The hot stage, the glass slides and the microscope must be kept very clean. Traces of liquid transferred from glass slides to the inner surface of the hot stage can give anomalous results. This method will not differentiate between the glasses with refractive index difference of less than 0.0003. Now comes to the dispersion staining method. By dispersion, we mean the splitting of visible light into its different colors. This is because of the fact that different colors bend with different refractive angles as they have got different wavelengths. Dispersion curve is a graph plotted between the changes in the refractive index to the wavelength. The dispersion staining method is based on the principle of dispersion. It is an analytical technique that takes advantage of the differences in the dispersion curve of the refractive index of an unknown material relative to a standard material with a known dispersion curve to identify the unknown sample. These differences become manifest as a color when two dispersion curves will intersect for some visible wavelength. It is an optical staining technique and does not require any dyes or stains to produce the color. When the conditions for dispersion staining are met, that is, once the glass is mounted in a liquid with a matching refractive index in the visible range, but with a different refractive index, then the glass has a refractive index which is high in the red part of the spectrum and which is low in the blue part. Liquids tend to have a steeper dispersion curve. The dispersion staining color is converted into a refractive index value that is added or subtracted to the refractive index value of the glass standardized to obtain the refractive index of the liquid. There are in general 5 types of dispersion staining techniques, or in other words, there are 5 different optical configurations for which the microscope used for dispersion staining. These configurations are backline dispersion staining, oblique illumination dispersion staining, dark field dispersion staining, objective stop dispersion staining, phase contrast dispersion staining. Each configuration has its own advantage and disadvantage. Out of these techniques, backline dispersion staining and oblique illumination dispersion staining were first reported in the United States, first by F.E. Wright in 1911. A brief sketch of all these dispersion techniques is as follows. Now, backline dispersion staining. This method is based on the fact that the particles behave like lens when immersed in a liquid, as they tend to be thinner at the edges than at the center. If the refractive index of the particle is greater than that of the surrounding liquid, then it behaves like a convex lens and will focus a parallel beam of light on the side which is opposite to the source of light. This, under the microscope, is seen as a bright ring of light called backline and moves in from the edge as the particle is dropped out of focus by increasing the distance between the stage of the microscope and the objective. If the stage is further moved closer to the object, then the particle will behave as a magnifying glass and the magnified image of backline appears outside the particle. For larger particles, this is indeed one of the best methods as it is least sensitive to other optical interferences. Now, oblique illumination dispersion staining. In this technique, the beam of light illuminating the sample is made to fall at an oblique angle through the sample. Although this will enhance the resolution of the structural details in the particle oriented at right angles to the incident beam, while some of the resolution of features parallel to the direction of beam are lost. As a result of this orientation of the beam, the relative refractive index of the particle and the surrounding medium becomes apparent. So, the wavelength for which the refractive index takes a higher value are refracted into the front lens of the objective from the side of the particle nearest to the side from which the light is incident. Thus, if the particle has a high refractive index for all the visible wavelength, then this side will appear dark, while the side which is farthest from the source of light will show all the wavelengths. Now, in dark field illumination dispersion staining method, the type of dispersion that takes place is due to the image of the particle which is formed by the refracted light, while the direct light incident on the sample is oriented at such an angle that it misses the front lens of the objective. The result is that the background is black, while the features of the object in the field of view that do not match the refractive index of the surrounding medium or the liquid appear as white. So, when a particle is mounted in a liquid that matches the refractive index within the visible range of wavelength, then those are refracted by the particle and are thus not collected by the objective. As a result, the image of the object is formed by the remaining wavelengths. These wavelengths will now combine to form a single color that can be used to indicate which band of wavelength is missing. This method is more difficult to interpret due to single color. Now, coming to the phase contrast dispersion staining. This technique will require a phase contrast objective. It takes into consideration the fact that the rays of the light that are not shifted in phase by the presence of the object are separated from the light rays which are shifted in phase at the back focal plane of the objective. These unaffected rays are significantly decreased in intensity. The particle will appear colored from the contributing wavelengths for which the mounting medium has a higher refractive index. Now, coming to objective stop dispersion staining. Now, this type is based on the fact that all the light unaltered by the presence of particles in the field of view is focused at the back focal plane of the objective. This method enhances the color effect, but the resolution of the particles is lost. That the glass samples are often found on crime scenes. As a result, a quick and reliable glass origin determination is a very important task in forensic laboratories. Although refractive index typically performs glass fragment identification, but refractive index data overlaps itself, and so often additional information is still required for glass fragments. So, the analysis of the elements which are present in the glass fragment under investigation can help in determining the chemical composition of the glass fragment and can help to identify the actual source of the fragment. The concentration of certain elements in glass chemically characterizes its source. In other words, the chemical composition of different glasses is different. That is, all glass products display variations in the concentration of these elements and contain small concentration of the trace elements also. The concentration of most of the elements is controlled by the manufacturer to impart some specific properties to a particular glass product. Thus, this can be particularly used to identify the product type of a recovered glass fragment. But even individual glass objects that have major element concentration, which are also controlled by the manufacturer, they will display visible changes and can give useful points for a forensic comparison. Element concentration may be used to differentiate among glasses made by different manufacturers or glasses from different product lines of the same manufacturer. Wet chemical analysis of glasses is time consuming because of large amounts of sample preparation, repetitive measurements and manual work in general. So, some alternate methods are used. Some of these instrumental methods have been developed by forensic scientists like inductively coupled plasma atomic emission spectroscopy, X-ray diffraction, X-ray fluorescence, Raman and infrared spectroscopy. Each of the observed and the measured values must be consistent between the questioned and known samples in order to prove the same source. If any of the findings differ, then the conclusion must be that the questioned glass sample cannot be associated with the known sample of the glass. Let us now discuss each of these techniques in brief. Let us first come to inductively coupled plasma atomic emission spectroscopy. Now, inductively coupled plasma atomic emission spectroscopy, also known as inductively coupled plasma optical spectroscopy, is an analytical method for the detection of trace metals in the glass fragments. It is a type of emission spectroscopy that uses inductively coupled plasma to dissociate the sample into its constituent atoms and ions. They return to the ground state emitting electromagnetic radiation at wavelength which is characteristic of a particular element. This emitted radiation is then analyzed by means of a suitable detector. When calibrated against the standard values, this technique provides a quantitative analysis of the original sample. Inductively coupled plasma is a type of plasma source in which the energy is supplied by electric currents which are produced by electromagnetic induction, that is by time varying magnetic field. This is the most common technique for elemental analysis with which almost all the dissolvable samples can be analyzed. This method of ICP is actually suitable for dissolved glasses and is a rapid and precise method. But the problem is that this process of ICP burns the sample. So, all the non-destructive examination should be complete. X-ray diffraction and X-ray fluorescence technique for glass analysis. Let us now discuss it. Now, X-ray diffraction and X-ray fluorescence techniques can be used both for elemental analysis of glass as well as for soil. X-ray diffraction methods are especially significant for the analysis of solid materials in forensics. They are often the only methods that allow further differentiation of materials under laboratory conditions. Minute contact traces and small sample quantities can be easily analyzed. Let us consider these techniques in brief. Let us first see the X-ray diffraction technique. The most important requirement for XRD technique is that the substance should be crystalline up to a certain extent, that is, the atoms in the sample should be arranged in a three-dimensional periodic fashion. This is represented by crystallographic planes. XRD actually occurs due to the scattering of X-rays from the set of planes following the Bragg's law, which is given by 2d sin theta is equal to n lambda, where d is the distance between the planes, n is the order of diffraction, theta is the angle of diffraction and or scattering, and lambda is the wavelength of the X-ray used. Now, as you can see in the figure, the most common method of X-ray diffraction is the powdered X-ray diffraction method, which is shown on your screen. Now, in this method, a collimated monochromatic X-ray beam is directed at the powdered sample, which is spread on a support. At least a few milligrams of sample is required. The sample holder is able to rotate. The X-ray gets scattered from the crystallographic planes of the sample. XRD pattern is specific to a particular element, or in other words, each element gives out its unique XRD pattern. So, it can be used as a signature of the material for comparison. The intensities of the diffracted beam in this method are recorded by a detector which is fixed on a movable carriage, which can also be rotated. The angular position is thus measured in terms of 2 theta, where theta is the angle of diffraction. Powder diffraction data are presented as a diffractogram in which the diffracted intensity is shown as a function of the scattering angle 2 theta. An instrument used for performing powder measurements is the diffractometer. Relative to other methods of analysis, powder diffraction method is a very rapid, non-destructive analysis of multi-component mixture without any need for separation of samples. Identification is performed by comparison of the diffraction pattern obtained to a known standard database such as the International Center for Diffraction Data's powder diffraction file. Coming to X-ray fluorescence. XRF is again a non-destructive technique which is used for chemical analysis of materials like glass and soil in forensics. The analysis is rapid and requires minimal or no sample preparation. In this technique, an X-ray source is used to irradiate the specimen. As a result, the ionization of the atoms takes place, that is, one or more electrons may be ejected out of the atom, but the energy of the X-rays used to irradiate the sample should be more than the ionization energy of the sample. These highly energetic rays are strong enough to remove even the tightly bound atoms. After the electrons are removed, the electronic structure of the atoms becomes unstable, and as a result, the electrons from higher orbital level, they will jump to the lower orbital level. Now, this causes the elements in the specimen to emit or fluoresce their characteristic X-ray, which are secondary X-rays. A detection system is used to measure the peaks of the emitted X-rays for qualitative or quantitative measurements of the elements and their amounts. This emitted radiation is characteristic of the element, which actually helps in the identification of the element. The instrument used is the XRF spectrometer. Coming to the Raman and infrared spectroscopy. Now, before going into the glass analysis using Raman and infrared spectroscopy, let us first have a brief introduction about Raman scattering or Raman effect, which is popularly known. Now, Raman scattering or Raman effect is the inelastic scattering wherein the kinetic energy of an incident particle is not conserved and some of the energy is either lost or increased. Now, when photons are scattered from an atom or a molecule, most of them are scattered elastically. That is, the scattered photons will have the same frequency or the wavelength as the incident photon, and this phenomena is known as Rayleigh's scattering. But a small fraction of the scattered photons are scattered by excitation, with the scattered photons having frequency or wavelength different from the incident photon, either higher than that or lower than that. This shift in the wavelength or frequency of the photon is what we call as a Raman shift. The higher wavelength side is also called Stokes Raman spectrum, while the lower wavelength side is also known as the anti-Stokes spectrum. Now, in the figure you can see the Raman spectrum or the Raman and infrared spectroscopy. Now, Raman and infrared spectroscopy are the two spectroscopic techniques which can produce very efficient and accurate detection of the pigments or color additives present in the glass. In particular, Raman spectroscopic analysis offers a very high discrimination and match certainty as glass transmits a relatively broad Raman spectrum due to the color additives mixed into the glass or organic protective layers which are used in car glass to prevent it from breaking. The use of infrared spectroscopy to determine the molecular structure had its roots established in the 19th century. Once the infrared region of electromagnetic spectrum had been discovered by Sir William Herschel in 1800, while the Raman effect was the first observed experimentally only in 1928 by Sir C.V. Raman, which resulted in Nobel Prize in 1930. In the past, the application of infrared and Raman spectroscopy in forensics had actually been very difficult due to the quantity of material that was required for the analysis, and also in most cases the destruction of the sample had to be done for the purpose of analysis. But with advancement in the instrumentation, both the techniques are capable of recording data from particles even in pictogram range. So, no destruction of sample is required. Despite of this, both the techniques have both advantages and disadvantages which tell one or the other technique is preferred for specific applications. For example, the presence of water or hydrated chemical species in specimens can hamper the mid-infrared analysis, while the optical dependence of Raman effect upon molecular polarizability rather than the dipole moment for the infrared means that the polar groups such as OH and CO are better seen in the infrared spectrum, whereas the homopolar groups, that is CC or NN, are better seen in Raman spectrum. A major factor in Raman spectroscopic application in forensics is the ability to overcome fluorescence emission, and this indeed the laser excitation at longer wavelengths from visible to the near infrared region of the electromagnetic spectrum. So, nowadays modern spectroscopic laboratories in forensics have such laser sources as the samples may be colored like the colored glass. The molecular fingerprint that is provided from the mid-infrared spectrum or Raman spectrum is well characterized, so it becomes easy to differentiate between chemically similar materials and not so in other cases. Now, let us understand how these two techniques work. In Raman spectroscopy, a monochromatic radiation of given wavelength lambda, it strikes the sample, which is the color glass or other seized evidence, and gets scattered in all directions. Now, most of the scattered radiation is elastic, but some of it is changed in wavelength, either increased or decreased, called the Raman shift, by an amount that corresponds to the sample's Raman active vibrational mode wavelength lambda v. The Raman shift can be positive, that is Stokes lines, or negative, that is anti-Stokes line. In this spectroscopy, it is the Stokes band that are measured, since these have higher intensity and involve transitions from lower to higher energy vibrational levels, while anti-Stokes shifts occur as a consequence of a few molecules existing in an excited vibration energy level undergoing transition to a lower energy level. In mid-infrared transmission setup case, the radiation from a broad band source passing through a sample is absorbed by the infrared active vibrational mode of wavelength lambda v. Both mid-IR and Raman spectroscopy are commonly used in microscopic based configurations in which the vibrational spectrometer is interfaced with the optical microscope system, which enable both visual and spectroscopic examinations. Out of the two, Raman spectroscopy offers some practical advantages over IR spectroscopy, as Raman spectroscopy is a scattering technique that uses a laser source, and so as such there is minimal requirement for sample preparation and presentation, and so the technique has a higher spatial resolution also. But still, Raman spectroscopy is considered to be less sensitivity technique in comparison to the IR technique, since colored glasses are made from different materials. So, the Raman effect, that is the Raman scattered band intensity and the mid-IR absorbance observed will be different for different glasses, and so a direct comparison with the existing data can be made. Now, refractive index is an important parameter with the purpose of examining glass samples in forensic science. Crime scene sample and standard samples are compared with the intent of knowing their source of origin. Glass particles are examined in the laboratory with the help of analytical and instrumental techniques such that their elemental composition can be determined, and which would further help in the process of investigation. With all this information, here we come to the end of today's lecture. Do keep in mind what we discussed today. I will be back with one more lecture in this series. If you want to learn more and enhance your language, you may log on to our website www.cec.nic.in for MCQs, quizzes, LORs, etc. Thank you for your time today. I will see you in the next lecture. Have a great day.